Okay, so your exam 3 is this Wednesday and Thursday. I have office hours today and tomorrow. Tomorrow's office hours are my last office hours of the semester. There will not be office hours Wednesday because I will be proctoring the exam for anybody taking it on Zoom during that time. Friday, there is no class, it's reading day. There's also something that the chemistry department does called the chemistry super study session. And usually that means that we open up rooms in the chemistry building and in Centennial, and faculty members from each topic area go and sit in a room and answer questions. This time, I assume it'll be digitally over Zoom. So I think it'll just be a Zoom meeting that is perpetually open. And older students also come to it as well sometimes. So you'll be able to ask some questions, maybe work through some practice problems. I won't be doing it this time because I have to be in training all day on Friday. So if you have questions for me on Friday, just know like I won't be able to touch anything all Friday, basically. Your final exam is Monday, December 7th. Oh, Sabina's saying it's not open for Tuesday, December 8th on Examity. I can fix that really easily. I'll do that after class. You should be able to, after class, once I fix this, sign up for a time slot through Tuesday, 11:59 p.m. on Examity. So make sure that you do that. If you want to take the exam by Zoom, you can do that Monday at 11 a.m. Please show up on time. The final exam is fairly long. It's not going to take the entire time that we're allotted for the final exam because I believe we're doing it ACS style where it's 70 questions in 110 minutes. So we'll probably actually start the exam a little after 11, but you need to be there by 11 to make sure that we get you set up. Please get some sleep over the next week. I can't even begin to emphasize how important that is. It honestly does not matter how much you study this week if you don't sleep at all. Your brain will not be able to function. I don't know how many of you guys read the announcement I sent out, but there have been studies that show that like driving sleepy is actually worse than driving drunk a lot of the time. And if you wouldn't take several shots of tequila before taking your exam, then you also shouldn't be sleep deprived while taking your exam. So this slide just has all the exam 3 topics on here. I'm not going to read this list out because you're definitely capable of doing that on your own, but this is here. That doesn't mean that, you know, there isn't going to be something a little outside of these ranges, but these are all the major topics. And I also tried to highlight the topics that are not necessarily in chapter 19 and 20, but that will make an appearance. A lot of them are from chapter 18. Oxidation and reduction. I didn't know how to sum that up without writing a whole paragraph, but oxidation and reduction of organic compounds. So think oxidation of alcohols, oxidation of aldehydes, reduction of carboxylic acids and their derivatives, reduction of ketone, reduction of aldehyde. So in that area. And as always, anything from Chem 2341 is fair game. That tends to include like substitution and elimination chemistry mainly, and addition to double bonds. Especially when it comes to your final exam. Okay, so I don't know why this is still here. That's weird. Okay. The review is either, you can find it either in an announcement or under practice exams. Okay, so these first questions that I put up here are specific for exam 3, and then I think I indicated where the final exam review starts. I want to skip ahead to that slide real fast because it talks about the final exam. And then we'll come back to the problems. The final exam is entirely multiple choice. So there's no short answer like there will be on your exam 3. It's approximately 70% Chem 2342 with about 30% Chem 2341. And what that means is 70% of the questions, the learning goal that's being focused on is 2342. That doesn't mean that you might not see a little bit of substitution, elimination, addition chemistry as part of those problems. So you might feel like there's a bit more organic one on there than what the learning goals are actually looking for. And Lastly, remember organic chemistry is cumulative in a way that your other classes, even your other chemistries, just isn't. So the final exam is an organic final exam, not just an OChem 2 final exam. Okay, so let's go back to, yeah, okay. Cool. So this is a good example of a problem that pulls stuff from other chapters. This is pulling chapter 17 chemistry in that first step. So if we take a carboxylic acid, in this case benzoic acid, and we react it with ethanol, an excess of ethanol and sulfuric acid, what are we going to get? Yeah, Michaela got it in the chat. This is a Fischer esterification. So after step 1, we will have an ester. When you're doing these types of problems on your exam, make sure that you have your scratch paper and that you are writing out the problems. A lot of you picked answers that were really, really close on the last exam, but all the answers are going to be kind of similar looking. So don't try to do OChem in your head, write it down. You're less likely to end up making mistakes. Okay, in the next step, we have, how many carbons is that? Ethyl butanoate with sodium ethoxide. What are we saying here? What are we trying to do? What is the ethoxide going to do to the ethyl butanoate?
It's gonna make a negative charge on the, oh my gosh, yeah, Claisen condensation. I couldn't remember the name.
Okay, yeah, so we're doing a Claisen condensation. Warren wrote deprotonate the alpha hydrogen. That's correct. I think Michaela said something along those lines as well. So we are deprotonating there. It will be in equilibrium. So you'd probably end up with kind of a mix of products, but the idea is that you're going to attack here. So one of the things that you should practice is drawing out the product of a Claisen condensation without having to draw out the mechanism and intermediates. So one of the quick ways to approach drawing out the product of a Claisen condensation is to remember that the piece that is attacked is going to lose the alkoxyl group. So it's going to be the keto portion of your product. Now this bond here is to this carbon. So we need to draw that on there. And then our ethyl group, oh, that's sloppy. Our ethyl group. And then off of our alpha carbon, we also have these other 2 carbons. So we're gonna have an ethyl group there. Okay, and then what is the ethanol there for?
Isn't that the driving force of the reaction?
Yeah, it's just a workup. Because remember, we're making ethanol, like this proton that's here is so much more acidic than this one was. So it's going to be deprotonated as well. And once you make the product, actually the product gets deprotonated and then reprotonated. So this is our product after steps 2 and 3, and therefore our final product. So this is a crossed Claisen. More commonly with a crossed Claisen, you would see a strong base like LDA with your enolate compound. Okay, this next one, we have an aldehyde and we have heat and acid. What are we saying? What are we doing here?
Are we making an acetal?
No, we're not making an acetal. You would need an alcohol for that.
Are we reducing it to a primary alcohol?
No.
Are we making a carboxylic acid?
No. Is sulfuric acid a oxidizing or reducing agent or anything like that?
Reducing agent?
No, it's none of those things.
Acid workup, right?
Yeah, this is just a source of acid. So if we have an aldehyde and we have acid and we have heat, what is this setting up?
An acid.
Condensation.
Yes, this is an aldol condensation reaction. Remember, this test is over chapter 19 and 20 mainly, so you should be looking for condensation reactions. Okay, so this is going to be our enolate carbon. Oh, that was going to be crazy. So remember that two molecules of the aldehyde are going to be reacting together. Right? We're going to create a new bond here, and it's going to create a bond to the carbonyl carbon. We know that our condensation product is going to be an alpha beta unsaturated carbonyl. So this is going to be a double bond. Like so. So one of the like fast ways to put together a condensation product is to draw out the aldehyde or ketone twice, but make the the alpha carbon overlap the carbonyl oxygen of the molecule you're going to attack. If you understand how this reaction works, this is a good cheat. If you don't understand how the reaction works, this cheat will still work for you the majority of the time, but there are a couple times where it might not pan out exactly right. So after step 1, we have our condensation product. Okay, and then in step 2, we add in sodium cyanide. What's going to happen?
Form a nitrile where the aldehyde is?
Not where the aldehyde is. So we have an alpha beta unsaturated carbonyl. And we introduced a nucleophile. Is it a strong or weak nucleophile?
It's pretty weak.
Weak.
Yeah, in the scheme of things, it's a weaker one. I mean, it's a good nucleophile, but we're comparing to Grignards, right? Grignards are much stronger. So what is going to happen? Where is this molecule? Where is cyanide going to attack on our alpha
Is it
saturated?
gonna attack the double bond on the saturated carbonyl?
Right.
Unsaturated carbonyl?
Is it going to attack in the alpha position or the beta position?
Of the beta.
Yeah. So this is going to do a conjugate addition. So steps 2 and 3 go together. This is telling you that you're going to attack and then you're going to have to protonate. So that double bond is going to be gone. Your hydrogen is still there. You don't have to draw it though, but I drew it for fun, I guess. And your nitrile will be there. So this is a conjugate addition. Okay. Did we work on these problems over the weekend?
My PowerPoint didn't even have a single problem on it. There was a glitch where I can't pull it up in PowerPoint.
Okay, if something like that happens, you'll let me know and I can send you a PDF.
Yeah, like it had the announcements and it had the topics, but then everything else was blank.
Okay, yeah, so I guess everything that I wrote in by hand. Okay, that's fine. This is just we're not gonna get through nearly as much in class evolve. Okay, so let's work through this one together. This one is kind of an overall redundant problem. It was just kind of fun for me to write. So that's where this came from. Step 1, we have a primary alcohol reacting with PCC. What is going to form?
Aldehyde.
Right, we're going to form an aldehyde. Okay. Step 2, you're taking that aldehyde and reacting with a secondary amine and acid. What are we going to form? All right, Justin says enamine in the chat, and that is correct. So aldehyde or ketone plus a secondary amine and acid is going to make an enamine. Okay. So we have an enamine now. Lithium cyanoborohydride. This is something that came from the chapter 19 notes, I believe. What is this reagent? What does it do?
Reduce.
Yeah, this is a reducing agent, and it's pretty mild, and it's going to be able to reduce this enamine to an amine. So this one is introduced, actually it's in chapter 20, now that I think about it, because it's amine related. You can reduce an imine, an enamine, or a nitrile with this reagent to an amine. So after step 3, we have a secondary amine. What happens when you react with hydrogen peroxide?
Reformation of the aldehyde.
No. This is from chapter 20.
Does it form an alkene?
No. I'm going to go ahead and give it to you guys. Okay, so we're forming an ammonium oxide. What reaction is this setting up for us? Yeah, Justin got it. We're setting up a cope elimination here. So step 5, you heat it up. You're going to be kicking that out. So step 5, we have this. So then I asked, is there a faster way to accomplish this transformation? Is there a faster way to go from a primary alcohol to an alkene?
Yes.
Yeah. Yes. So this is from OCHEM 1. There's a way to go directly between these two.
Don't you just like add, isn't it just an acid and heat?
Mm-hmm. Yeah, so this is acid catalyzed dehydration. Yeah, so I wrote all these because these are the reactions you need to know, but ultimately, if this were a synthesis that you set up in a lab, you'd probably get fired. It's very wasteful. It's not a great synthesis. Okay. This next one, what are we setting up here?
Is it Gabriel synthesis?
Yeah, this is the Gabriel amine synthesis. What is the product of this reaction going to be? What functional group? Yeah, it's going to be an amine. Can we be more specific? Yeah, primary amine. Oops. Gabriel, this is going to give us a primary amine. Okay, so step one, what happens when you react phthalimide with potassium hydroxide?
Doesn't the H get replaced out with the potassium?
Yeah, we're just deprotonating it. You don't need to draw the potassium in. That's just showing the counter ion. So we've deprotonated it now. So now it has 2 lone pairs on it. It's become a better nucleophile. Does it have to be potassium hydroxide to do this? Could most bases probably do this? The answer is yes.
Yeah.
Yeah, most bases could do this. So if you see something else at the beginning instead of potassium hydroxide, don't panic. It's just, it's still, if it's a base, it's still just going to deprotonate. Okay, so then what happens now that we deprotonated phthalimide? We add in this alkyl halide. And what happens?
It attacks the alkyl halide.
Right, where does it attack on the molecule?
The carbon of the halogen.
Right, so yeah, the carbon that's next to the halogen, the alpha carbon. What type of reaction is this?
Isn't this just like an SN2?
Yep, this is an SN2 reaction. Just a straight up nucleophilic substitution. Okay, be careful with your carbons. This is one of those places where people start to lose a lot of carbons. So there's 1, 2, 3, 4 in the main chain and a methyl group. So 1, 2, 3, 4 methyl group. Make sure you do not lose carbons. Okay, and then step 3, what happens? What's N2H4?
It's the Wolff-Kishner.
So it is used in Wolff-Kishner, but this is not a Wolff-Kishner reaction. What is that compound called?
Hydrazine.
Yeah, hydrazine. And what's happening here?
Are they going to attack the ketones?
Yeah, so we're going to open up our ring and release our primary amine here. So the phthalimide, whoops, I shouldn't have drawn that at such a small angle. Is going to end up looking a little different. So the hydrazine has inserted itself there. And we also have our primary amine, like that. Okay, so let's say you're doing this problem on an exam. On an exam, you're going to have a multiple choice selection of amines as your product. I'm not going to draw this because that's not the goal of this reaction. So what is the fast way to figure out what your product is going to be so you don't have to draw all this out?
Just
Add the amine in place of the bromide.
Right, so look at your alkyl halide, cross out bromine and draw in an NH2. Now that doesn't mean that you don't have to understand the mechanism because there are going to be multiple choice questions that kind of ask you about the mechanism. Maybe not of this reaction specifically, but of reactions in general. On your exam 3, I can do short answer. So maybe this is something I'm going to ask you about. So just keep that in mind. Okay, next one. We have ammonia and H+ in excess. What are we doing?
Is it being reduced to a primary amine?
Nope. No, we're not creating an amide because we have a ketone. Protonation would be the first step of the mechanism. But what do you get if you react ammonia with a ketone? Justin asked.
Primary amide.
No. Justin asked as a side question, would it create an amide if it was a carboxylic acid? If you reacted a carboxylic acid with a massive excess of ammonia in acid and heated it up to a very high temperature, put it under pressure, yes, you could make an amide. Typically, we don't make amides that way. I usually ask you guys to go through the alkyl halide. Let me change this idea. What if it was a primary amine? What functional group would it make reacting with a ketone and acid?
An imine?
Yeah, it would make an imine. The same thing happens with ammonia. It's going to go through the exact same process. Let me erase that so I can use my space. Okay. Also looking at this, I'm pretty sure I meant to add in a reduction. Sorry, I was trying to get this to you guys quickly. So there's probably some sort of reduction. Let's go with lithium cyanoborohydride to turn this into an amine. Okay, so it's an amine. And now we add in a massive excess of methyl iodide and pyridine. What's going to happen?
Are we going to add 3 methyl groups onto the nitrogen, forming a positively charged nitrogen?
Yeah. So remember that when amines are reacted with alkyl halides, they do not have a lot of control, especially if there's an excess of the alkyl halide and it's highly reactive, such as methyl iodide. You're going to methylate that all the way to a quaternary ammonium. Okay, so then we have potassium hydroxide and heat. What is this asking us to do? What does heat imply?
Elimination.
Yeah, remember heat implies elimination. Same thing when you're looking at an aldol condensation. That last step is essentially just a dehydration and elimination. So that's something that you can look for. What type of elimination is this?
E1.
I'm looking for a named reaction, actually. It goes through an E2 process. Yeah, this is a Hoffman reaction. I can never remember if it's 2 F's or 1. I think it's spelled 1 F, 2 N's. I don't know. We used to have a faculty member here with the last name Hoffman, and that messed me up forever. So, okay. So the thing about the Hoffman elimination is that it forms a specific product, right? So there are 2 possible elimination products, right? We could eliminate using this proton and create this product, or we could eliminate using this proton and create this product. Let's call this A, let's call this B. Which one does Hoffman make?
The least substituted.
B.
Tryptonate, the least substituted, it makes B, right? So that's the tricky thing about the Hoffman elimination, is that when you have that quaternary ammonium and you add in potassium hydroxide, or you can do it with sodium hydroxide, and heat, you're actually going to make the less substituted alkene. So it's a cool process if that's what you're aiming for. Okay, so Hoffman elimination. Okay, we have chromium 3 oxide, and we have 1 molar sulfuric acid. What are these conditions? Yeah, Justin says strong oxidizing, question mark, yes.
Jones reagent.
Yeah, these are actually the pieces of Jones reagent. So Jones reagent is, whoops, CrO3, sulfuric acid, and water. So by adding in 1 molar sulfuric acid, we have sulfuric acid and water. So this is a strong oxidation. So what is our product in the first step? Yes, Wesley said it, several people said it in the chat. We're making a carboxylic acid, and then I heard it out loud as well. Good job. Okay. And then we react with SOCl2. What is the name of SOCl2? What do we call that?
Thionyl chloride.
Thionyl chloride. Whoops. Sorry about that. Yeah, remember, I love a good word problem. Okay. I usually throw like 1 on your exam just to see if you're using terminology when you're practicing and stuff. What happens when you react a carboxylic acid with thionyl chloride?
Chlorination of the carboxylic acid. Remove
Right.
remove the OH, replace it with chlorine.
Right, we're making an acyl chloride. Okay. And then we react with an excess of ammonia. What's that going to make?
An amide.
Mm-hmm. Okay, and then step 4. We're reacting with an excess of bromine and hydroxide. What is that making?
Isn't that Hoffman rearrangement?
Yeah, so what is this going to do for us? What does the Hoffman rearrangement do? So yes, Justin said it's going to make an amine. Yes, it's not a reduction though, because if we just reduced it, like with lithium aluminum hydride, we would end up with this compound, right? What's our product going to look like?
Secondary amine.
Is it going to turn that cyclohexene into a benzene ring?
No. What's the difference between this product and our product? Yes, Justin wrote it in the chat. It's going to remove this intermediate carbon. So our product is going to be cyclohexane. Whoops. That was the worst. Okay. And remember, this is still a primary amine because there are 2 hydrogens on there and only 1 thing attached to it. So they're both primary amines. Justin said it sneaks up on you. Yes, this one is kind of tricky. So the cool thing about the Hoffman rearrangement is that if you can recognize these conditions with the amide, just cross that out, just draw a new bond that skips right over the carbonyl and you're good. So yeah, don't let it be harder than it is. Okay, this next one, we have an aldehyde. Are there any questions? Are we doing okay? I haven't been pausing because I'm trying to get through as many of these as I possibly can.
Let's keep it going.
Okay. So we have an aldehyde and we have sodium hydroxide and heat. What are we doing?
I'm assuming an elimination.
E2 reaction.
Yeah, so we do have heat, so that implies elimination. We can't, like, there's nothing to eliminate though, right? Yeah, so Justin is suggesting aldol in the chat, and that's correct. This is an aldol reaction. Is it going to do the addition or condensation?
Condensation.
Right. So aldehyde or ketone, right? These are the flashcards that you need to be making. Acid or base, especially if it's strong, plus heat, condensation. I guess we want to put that word aldol in there too. So we are looking for an alpha beta unsaturated carbonyl as our product. Sorry, my pen is lagging a bit, so my handwriting is getting worse. I can't see what I wrote already. Okay, so you want to practice this again. Think about drawing out your product quickly because you're not going to have that much time on your exam, especially on your final. So draw out the molecule that's going to do the attack. Right, so this is our attacking molecule. This is where our enolate is going to form, and it's going to attack the carbonyl carbon of another molecule, right? So this is the new bond that we're forming. And you can use that trick that I suggested from earlier. You know, just go ahead and draw out your compounds again, as if, oh, I wish I hadn't drawn that so big. One second. As if the carbonyl oxygen was overlapping with the carbonyl carbon of the other molecule, or of the alpha carbon, sorry. So that is our product. And I guess, sorry, it would be the trans product that would be favored if we did this. Especially since that's quite a bulky situation. Okay. Let's keep moving forward. Okay, this one is kind of a deep dive. We have a nitro group, and we're reacting it with iron and hydrochloric acid. Justin says that Leia Force I has some great videos. Yes, I agree. That's the site that I share most often with my students, and I put some on some of your earlier resource pages. If you need to watch more lectures after you've watched my lecture videos, definitely visit Leia Force I. If there's any chemistry on there that we're not covering, just skip over it. Okay, so a nitro group reacting with iron and hydrochloric acid. What are we doing? Nitrobenzene with iron and hydrochloric acid. Yeah, Wesley says reducing it to the amine. Yes. So this is one of those kind of one-off reactions. You take nitrobenzene or a nitrobenzene derivative and react it with iron and hydrochloric acid, you're going to end up with an aniline or aniline derivative. Okay, so then we react with sodium nitrite, NO2, and sulfuric acid. What are we doing?
Are we doing a nitration?
Not a nitration. The condition for nitration, you might recall, is HNO3. Oops. Sorry, my computer is freaking out. So you're looking for acids, right, for that one. And just acid. Yeah, Wesley says creating the diazonium salt. Yes, that's exactly what we're doing. So you react the amine with nitrous acid. So that's what's forming between sodium nitrite and H2SO4. We are forming nitrous acid so that we can form the diazonium. Okay, and then what does this do when we react it with copper cyanide, copper 1 cyanide?
Turn it into a nitrile.
Right, so this is an example of a Sandmeyer reaction. So we are doing a replacement by diazotization. So we've created a nitrile. And then if you react a nitrile with nickel in excess of hydrogen gas and heat it up to 140 degrees, what are we doing? As it says 2 equivalents.
Are we going to remove the nitrile?
No, we're not going to be able to remove it. What's going to happen to all these pi electrons if we react it with hydrogen? Alex says the bonds break. Yes, but what else do they do? Let's think about it. We take a nitrile, which is a lot like an alkyne, and we react it with hydrogen and heat it up. What's going to happen?
Create an alkene.
Well, so if we did this with a nitrile and we had, an alkyne and reacted it with 2 equivalents of hydrogen, it wouldn't stop at the alkene, right? Yeah, we'd end up with an alkane. So what's the analog reaction for a nitrile?
CH2 NH2.
Right, this is a reduction to an amine. So you call this benzylamine would be an acceptable common name for this. Okay, the next one is a synthesis problem. Let's see what else. Okay, it's 1048. I'd rather skip over that synthesis because that was largely, well, I guess it uses Sandmeyer chemistry. I want to do something more challenging. Okay, let's crank this out real fast. It's not super fast, but let's work on these for a second. So if we take acetone, which is a ketone, and we react it with sulfuric acid and heat, what's going to happen?
Aldol condensation.
Right. Okay, and I realize I'm cranking through the product. You should definitely take the time to work that out on your own if you need to. Okay, so we've created an alpha beta unsaturated carbonyl. So remember, use your context clues when you're taking a test. So if we have this alpha beta unsaturated carbonyl, and then I start throwing nucleophiles at you, like this is gonna be an enolate, this is potassium cyanide, water, Grignard. I'm testing to see if you know where different nucleophiles are going to attack on this molecule. So that's a good hint to you as to like what's going on here, and that you should have done the condensation in case you did the addition instead. So which carbon does potassium cyanide attack at? Alpha, beta, or carbonyl?
Beta.
Yeah, it's going to attack in the beta position. This step 1 is going to create an emulate. Where is that going to attack?
The carbonyl carbon.
The oxygen. Carbonyl oxygen.
No, so this is going to attack in the beta position as well. This is going to be a Michael addition because it uses an enolate to attack an alpha beta unsaturated carbonyl. Where does water attack? Is water what we would consider a strong nucleophile?
I'm gonna attack the oxygen.
No.
Oh no.
There are 2 places that we can attack on this molecule. So even though I asked about alpha, like I just said that it's not going to be attacked there. It's either the beta carbon or the carbonyl carbon, right? There's only one type of compound that we talked about that will attack at the carbonyl carbon. Is water that compound?
No.
No. Okay. What about Grignards? Where do they attack?
The carbonyl carbon.
Carbonyl.
Okay, so Grignards and alkyl lithiates can attack the carbonyl carbon. So that's the first step to all of these, and then it's just a series of fun. Yeah, so we are out of time. It's 10:51. I have office hours today, so if you want to come to office hours, we can work through more of these problems. I will record the answers to these. I can guarantee you, though, I don't have time to work through all of these on video before exam 3, but I will do it before your final exam. So if you have questions on any of these problems, please come to office hours or shoot me an email. If I finish the exam really quickly or faster than I think I will record them, but please don't count on that for exam 3. I can write out the answers, so I won't be able to make a video before exam 3. But I will write them out for at least the first portion. Okay, I'll see you guys either in office hours or at the exam on Wednesday, or maybe not at all again.
Thank you.
Thanks, guys. Yes, Megan, we can check your grade during office hours, or if you want to stick around now, and if everybody else leaves, we can do that now if you wanted to. I know.
Well, I wasn't sure if you had to go right away.
Oh, good point. Actually, I do.
Okay.
Yeah, I have to be somewhere at 11. But if you just want to know about your grade, we can look at that real fast.
Okay, cool. Thanks.